Hi everyone, welcome to Algebra 2 Honors Functions in Real Life. So Chapter 2, 2.3, let's get started. So our learning targets are being able to model graphs to real life situations. So first we're going to start off with a warm-up and we're going to talk about function, notation, and graphs. Now remember the other day when we last met and we talked about f of x being a function, defining a function, also f of x representing y. We don't really use y equals when we're talking about functions because we want to say, hey, this is a function, you're going to use f of x. That represents that. So the x would be this value inside here. So if I'm replacing x with a value, that's going to be within the parentheses. So this is saying, well, what's f of 0? So we're looking for f of 0. Now we know that 0 is right here. So when we're trying to find f of 0, that's right here. So when x is 0 right here, then y is going to be 3. So you would say f of 0 is equal to 3. Likewise, if I'm saying f of 6, so f of negative 6 for the first problem, I'm going to look at negative 6. So when x is negative 6, y is negative 3. So you're just looking for that value on the graph. And those are actual points, remember. Find f of 6. So now I'm going to look for x is equal to 6 because remember, that's your x. So when x is 6, what's y? So f of 6 is equal to 0. F of 11, so what is f of 11? So we're going to find x at 11. Here's 11, and at 11, it's 1. Is f of 3 positive or negative? So where is f of x? So f of x, where I'm at 3, 1, 2, 3, and this is this value somewhere right around up here. So because it's up above the x-axis, it is positive. F of negative 4, if this is negative 5 here, so negative 4 is about here, that would be down here below, so that's going to be negative, okay? For what values of x is f of x, so that's y, equal to 0? So they're asking me, look for where is y equal to 0. That's what they're looking for. So y is equal to 0 here. Let me erase this so you guys can see this a little bit. Okay, so y is equal to 0 here at 6. So you would say at x is equal to 6. Y would be 0 at 10, at x is equal to 10. And y would be 0 at x is equal to negative 3. For what values of x is f of x greater than 0? So they're asking, where is y greater than 0? So not here, because that's a negative value. And they're asking you for greater than 0, not equal to 0. So this would be out as well. Greater than 0 would be at x equals 0. Greater than 0 would be at 2, 4. So that would be where x is equal to 2. Greater than that would be where x is equal to 4. Not here, because they don't want it equal to 0. It has to be greater than 0. This is below. This is at 0, and the last one would be at x is equal to 11. What is the domain? Now remember, we talked about the domain last class. The domain goes from left to right. It's all those values of x, those input values of x that go from left to right. So the leftmost, this, because it's not going to infinity, it actually has a little solid circle here, is going to go like that. And so the leftmost for a domain would be negative 6. Now remember, that is a bracket because it is containing that point. And then all these values would go up. These values would all come down, right? Pop down to the x-axis. These would all come up. It's sort of like fill in a line onto the x-axis. And then the greatest value here in my domain would be at 11, and that would include 11 as well because it's that point, because that value is solid. To find the range, remember we go low to high. Domain, you go left to right, but the range, you go low to high. So the lowest value here is negative 3. Now you got to ask yourself, at negative 3, does this value have a solid dot? Yes. So that point is solid. So there's not an open circle, it's solid. So you would say negative 3. And remember, all those values are now going to the y-axis. So before they were going down and up, these values now are coming to the left. We're all of those values are migrating over to the y-axis and sort of filling it up like that. And you're asking yourself, what's the lowest value, which is negative 3, and what's the highest value? And it looks like it's 4 right here. So negative 3 to 4, and that's how that goes. What are the x-intercepts? Well, actually, I can't see anything right now, so I'm going to erase this. The x-intercepts are where my graph crosses the x-axis. So my graph crosses my x-axis where y is equal to 0. And those are these values up here. You see that? These are all my y-intercepts. Oh, wait. Hold on. Is that it? Where is it greater? Nope. Actually, that's not right. My x-axis, here they are, right here. X is 6. We've got x is 10, and x is equal to negative 3. Because you look at it, where are my x-intercepts? That's where my graph crosses the x-axis. So it's at negative 3, comma 0. X-intercepts would be at 6, comma 0. And my other x-intercept would be at 10, comma 0. My y-intercept, I just have one, where my graph crosses the y-axis, which is right here at 4. So where the graph crosses the y-axis, you would just say, what is the y-intercept? The y-intercept is 4. Okay. Uh-oh. All right. Okay. So we also talked about the domain and range for each graph. In interval notation. So when we're writing the domain and range, remember, domain goes left to right. So if you think about it, see how this is an arrow here and this is a dot? When I'm going left to right, the value to the left, that's going to keep going. So that's negative infinity to all the way to the right, which is 5, and that's going to be a bracket because this is solid. My range goes low to high, so that's going to be negative infinity, because remember, this is just going to keep going down. And so those values are going to squish to the y-axis. And when this squishes to the y-axis right there, that looks like a 2. So it'd be negative infinity to 2, and including 2, because this is a solid circle. Now, for this problem here, the domain going left to right is from negative 5. Now, keep in mind, even though I'm saying negative 5, maybe it's a little hard to see, but that's an open circle there. And right here is also an open circle. And so my values go down and up. So this would be negative 2. So negative 5 to negative 2, and not including those values. Likewise, my range goes low to high. So this low value here is going to be negative 4. So they're going to go negative 4. And the highest point here looks like it's 4. So up to 4. For this problem, left to right again, this looks like it's negative 4, but it's an open circle, and if you can't see that, that's an arrow. So this one's going to go from negative 4 to, and that's going to keep going, right? This is just going to keep going up, and you're just never going to get that x value. So that goes to infinity, and my range goes low to high. So this low value here is negative 1, but it's because it's an open circle, it's a parenthesis, and then it's going to go also to infinity. For D, the last value, to find the domain, remember, it goes left to right. This value is not my leftmost value, because see this keeps going, and so that's going to just keep shooting out that way. So my domain going to the left is negative infinity, but my domain going to the right is right here. That's where it's going to end, and that's 3, and it's including that value. My range goes low to high, so this is this value, which is solid. So that's going to be bracket, negative 2, and then going up, this is just going to keep going up, up, up. So that's going to be negative 2 to infinity, and remember, infinity is going to have that parenthesis. So we're going to start some mathematical relationships. And so using these are basically, you're trying to model something in real life. So within math relationships, the value of one quantity is going to depend on the value of the other quantity. Like, can I go to the movies? Well, it depends if my parents say yes or no, right? So that it's like something depends on something else. So when you're looking at the values in this relationship, it looks like whatever this value is here, that's going to depend on this value here. Meaning this value, my y value, is my dependent value. Which one? This depends on this. So this is going to dependent. And this one then, if that's depending on something else, that means this value down here is my independent value. Okay? something that this would work on, what kind of things would this graph depict? You could say, well, days depending on weeks. We have way more days than we have weeks, right? Ocean tide and time. So, I mean, we've got like a lot of different things that we can use, and you can come up with something, you know, completely separate. There's just so many options for that. We're going to consider the following graph right here on the right. We have the number of wheels here, okay, and we have the number of cars. Now that should make sense because the number of wheels, right, the number of wheels depends on how many cars we have. How many cars we have, right? And so that looks reasonable. That is a reasonable graph. So that, and you know, that's what we're creating. So you are to create a table that shows this relationship. So let's say we have how many cars? Well, how many wheels is that going to be? So if we have 2 cars, it looks like we're going to have 8 wheels, right? If we have 4 cars, then it looks like we're going to have 16 wheels. Okay, so you fill in this graph and then try to write a description that matches this graph. Okay, so take a moment to do that, pause the video, and then, okay, move on. So we've got this graph. Possible answers are, if we have 1 car, we have, if we have 1 car, we have 4 wheels. If we have 2 cars, we have 8 wheels. So we just filled this in right here. And the description that matches the graph, the number of wheels, depends on the number of cars. So just to reiterate, this value here, the y value, depends on my x value. My x-axis is independent, so it can stand alone. So most of the time, I will say that the independent variable is time, but not always. And I think I'm going to do an example where time is not always the independent variable, but most of the time it is. The independent variable, which is this one down here, is basically the variable the researcher changes application. So like this is basically, if I water the plant, then it will grow. The plant growth depends on how much, you know, water that I get or something like that. So I mean, like, you can arrange it how you want to say it. You could well, that's going to, the number of leaves depend on, you know, the growth, etc. So you've got a lot of different varieties of what you can say. What your objective is for this lesson is to try to draw a reasonable graph, something that makes sense to you and that it has the dependent and independent variables. And that's what you're looking for in this. So here we go, our objective, giving a situation from the real world where the value of one variable depends on the value of the other. I want you to sketch a reasonable graph showing the relationship. So this one basically says the time it takes you to get home from school and the speed you drive the car are related to each other. So your job is to sketch a reasonable graph showing this relationship and label your graph. So pause the video. I want you to try to figure out what do you think would be a reasonable graph to show this relationship, okay? And what do I label my axes? What depends on what? So take a minute and we're back. So what I'd like you to do is to just talk about what do you think depends on what? Do you think the time it takes to get home depends on the speed? Or do you think the speed, how fast I'm going, depends on the time it takes me to get home? That doesn't even sound right the way I said it, right? So actually this one, even though time is usually independent, in this case, time is the dependent. The time it takes for you to get home depends on how fast you're going. It depends on your speed, okay? So in this problem, you're sketching a reasonable graph. Now you got to remember, I have no time. So at 0 time, well, at 0 speed, no time has gone by, right? So basically, we would start like a little bit off of the axis, okay? And then the faster I go, the less time it's going to take. So as I'm moving over this way, right, the less time it's taking. So this would be something like this, right? Okay, and then what does this depict? This just basically says how long it takes depends on how fast I go. Yeah. Okay, so what the answer is here is basically saying, hey, since it always takes you some amount of time, no matter how fast you drive, the graph never is going to touch the horizontal axis, because if you're going no speed, then time, is you've already gotten there. As far as this one up here is, if you're not going any speed, if your speed was 0, then no time had passed. So that, what we call these values here are actually asymptotes. See this right here? This is an asymptote. This means that my graph is going to say get super, super close to that, but never touch it. Likewise with this. It's going to get close, 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 but never touch. Okay. Oh, by the way, asymptote is a Greek word, and it just basically means not coming together, so it never catches up or meets up with that. So let's try this one. You take a hot pocket from the freezer, you put it into a hot oven. Okay, so it's going to start off super cold. The temperature of the hot pocket depends on, so they're telling you what depends on what, right? So they're telling you that the temperature, okay, depends on how long it's been in the oven. Now, how long is actually time, right? So the time in the oven, how long it's been in the oven. So the longer, as it goes this way, the longer it's been in the oven, the hotter it's going to get. So sketch a reasonable graph, label your graph. So we already started off with temperature and time down here. So what I want you to do is, again, pause the video, take a minute, and try to draw your graph. Okay, so hopefully you did that. Sketching a reasonable graph. Think about this. When you took the hot pocket out of the freezer, it's super cold, right? So like that would be here, cold. But then this is temperature at 0, right? So that means that it's super cold, but as soon as it gets hot, like it's going to go probably up, right? Because it's going to get hotter and hotter and hotter, but then how hot is it going to get, right? So you've got to think about this, that at some point it's not going to go any hotter than how high you set the oven for. So let's see if we got that right. Okay, yep, that looks like it, right? So we started out the refrigerator at 0, that looks like that, and then went up because as the oven got hotter, right, the temperature rose, and so therefore the hot pocket got warm. But keep in mind, whatever temperature, let's say you set it at, I don't know, 300 degrees, that's going to actually stop right there at 300 degrees. It's not going to ever like get to that, okay, or get more than that either. It's not going to touch it either. It's going to be always a little bit less. Here's another example. The price you pay for pizza depends on the diameter of the pizza. So let's say we have a small pizza, right? That value, this is my diameter, excuse me, that's my radius. My diameter cutting across like this. Let's say my diameter is 8 inches. Well, if I have a bigger pizza like this, right? Here's my radius coming across, here's my diameter. Let's say I have a, 12 inch or 15 inch, whatever the pizza is. The price you pay depends on the diameter of the pizza. So basically, they're telling us this is the price. This depends on, the price you pay depends on the diameter of the pizza. So draw a reasonable graph which you think depicts this problem. Pause the video, try it, start it up again, okay? So in doing that, hopefully you paused and then restarted. Basically, what you're looking at is this right here. You're looking at the price you pay right here. It's going to start out, why is it starting out at 0 here? No value here. If I don't pay anything, if I pay no money, right? No money, I have no diameter. So basically that's what that's saying. But the bigger the diameter, the more expensive my pizza is. Of course, unless I, went somewhere that had awesome pizza, like in Chicago, they have the best pizza, but places like that. Anyway, all right, so here we go. As you play with a yo-yo, the number of seconds that have passed and the distance from the floor are related. So this one, they're not telling you what's what. So take a moment, pause the video, and try this yourself. As you play with a yo-yo, the number of seconds that have passed the yo-yo's distance from the floor are related. So you have to ask yourself, what are my two things? We've got seconds. My two variables are seconds, and it looks like distance. So your question in your mind is this. What are you asking yourself? Are you saying that the seconds that have passed depend on the distance from the floor? Or are you saying the distance the yo-yo is from the floor depends on the number of seconds that have passed? Okay, so take a minute, try to draw a reasonable graph. Okay, so you're back. Hopefully, what you decided was in this problem that the distance was your dependent variable, because the distance, your graph, your yo-yo is, because like you start off with a yo-yo, you go up, start up high, and then you throw it down. That up there is going to start high, right? It's going to drop down, it's going to come back up. And what does this represent here? This right here, that should, I mean, I know that this is time has passed, but as well, this is actually representing the floor, isn't it? And it's not really going to touch the floor. I guess you're going to break the yo-yo, but that's what that is. So here's our time. So the longer that this is passed, right? The longer the time has passed, the distance is going to vary like that. And so this is actually what we call a periodic function, because it's just going to keep continuing as long as you are playing with the yo-yo, right? So that's it for today. Your homework is basically matching your graphs to stories. It's a worksheet, and also a second worksheet that is 2.3. I hope this helped, and please email me if you have any questions at all. See you tomorrow.